स्लाइड इसी से चेंज हो जाएगा. सपोर्ट नहीं कर रहा.
हाँ यस. रुक जा. Which folder? Top GAC, top GAC.
और ये स्लाइड चेंज हो रहा. स्लाइड चेंज होने का. अच्छा नहीं, इससे हो रहा चेंज. हाँ बस ठीक. Okay, so thank you very much. So I am not your guest. I also belongs to Jabalpur, so it's great privilege for me to share a small piece of work what I did at Mizoram. So I want to share with you. So I saw mostly audience is students. So I discuss from the student point of view, first what we did and how we prepared the samples. Then further will come for characterization and application part also. So it's good to see you at GAC. During I studied when I was in student at RDVV, so I did my research here under Professor Lakshman Pandey, who was working on NMR. He was basically from BHU Varanasi. He did his postdoc, PhD from IIT Kanpur, and later postdoc from Canada. So it's good. So what I am going to share you, it's just a multifunctional materials. So what we did in our institute under the SERV project, we start preparation of materials by the process we call the solid state reaction technique. Although you can prepare same material with the sol gel or the co-precipitation, later we'll did that part also, but due to time constraint, I cannot discuss all the method here. But if you are interested, later we can share our interesting results on the other method also, because it's still on that field, still our work is going on. Because main motto of this study behind is that we have choose the material called bismuth ferrite. If you understand the meaning of it, so we write it generally called BFO or BiFeO3. So if you see that structure, so it's simply AbO3 type of material, or simply we call perovskite structure, where A side bismuth is there, B side iron will be there, and oxygen at its place. So if you see its structure, so it's generally rhombohedral in nature. If as a student you studied about the seven type of crystal structure, so one type of rhombohedral is there. So once we start doping of rare earth, why we doped rare earth? Because we want to see the applicability of the material, and especially for the electronic devices. So if you see the application for electronic devices point of view, so this bismuth ferrite is having the main drawback we call the high leakage current. So if device you are having the material with high leakage current, then you cannot go for the multifunctional applicability of such type of a material. So you have to remove those drawbacks which are inherent property. But why we use bismuth ferrite? Because as I told multiferroic word here, so I just tell you first what is the meaning of multiferroic and what property we want to going to study in it. Okay, so this is the basic outline of my lecture. So if you see the work which that the outline I have given, why we have choose BFO? Because it's having lot of application in spintronic and the electronic devices or the memory device, FRAM, DRAM, whatever there. So if you see the multiferroics means the material which exhibits more than one ferroic order. So one ferroic mean either it may be ferromagnetism, ferroelectricity, ferroelasticity. Even now people they have developed ferrotoroidicity also. But I didn't approach that part, so I cannot discuss. But here in this work, as the definition tells us more than one ferroic order. So we have seen two ferroic order here. One is ferromagnetism and another is ferroelectricity by doping the rare earth material on the pure bismuth ferrite. That is the main work. But I didn't try this elasticity. But if somebody is from mechanical engineer, they can do it because it's just a deformation. It takes place on the application of stress. So if you have some mechanism to study those things, so you can study the ferroelasticity also. So this is diagram which shows you multiple phenomena. If you see first one, so on the application of electric field, development of polarization is there. On the application of magnetic field, magnetization is there. And on left hand side, on the left hand side, mechanical strain and stress relation, that is the ferroelasticity. So this whole pictures give the concept of the multiferroic phenomena of the material. Now, what method I have used, as I told you earlier, that is the solid state reaction technique. So, in solid state reaction technique, basically we'll take the powder form of material, and basically it is in the form of oxide or carbonate. So, as you know that it is a heat treatment. So, during the heating process, it will come out in terms of oxide or carbon dioxide and any other gases. So, you can evaporate those things. Then this mixing and grinding will be done either by hand, those who have from chemistry also. So you have seen the mortar and pestle. So you put all the powder in the stoichiometric ratio and try to grind it just like a grinding machine for 2 hour, 4 hour, whatever time you will decide for the proper mixing of the chemicals. Then after that, if you don't want with the this one, so you can do it with the mechanical process. But for that process, you should require the instrument we call the ball milling process or the high energy ball mill, where you can put your powder, fix the RPM, decide the time for the movement of the balls. So balls will be sometime zirconia balls or the steel balls will be there. So you can decide the balls as per the chemical or reagent you are using for the fabrication of your material. So you can just on the machine fix the time RPM, then it will automatically rotate and mix it. So you can not do much hard work from your hand. That is the advantage. But the machine is also costly. If you take a single jar ball milling machine, so it may be around 14 to 15 lakh. If you take double jar, so it may be more than 20 lakh, and so on. Then after that, once you do the proper mixing and satisfied that all the chemical they have mixed in, then so you can check with the XRD to see the structural phase. Why XRD I will discuss later. But if you are not satisfied the formation of the X-ray analysis, then again you have to repeat the process. And whatever calcination temperature is required, always remember that whatever heat treatment you are doing for any chemical, it should be always be lesser than the melting point of the material. Otherwise, due to casualness or the don't know the actual value of the melting point, you increase the temperature of furnace more than 1,000 degree, and then suddenly chemicals will be melt. So don't do that. So before starting the preparation, you should properly know what will be the melting point, when it will mix, how you will check the formation, how much time is required for the proper thermal analysis or the chemical mixing of the sample. And if you satisfied with the XRD, then you will further move for the other process. Like if you need the powder in terms of pellet, suppose you want to do the electrical measurement, so for electrical measurement, you need LCR meter or the impedance analyzer. So again, you need you cannot put directly powder to take the dielectric property, dielectric constant or the dielectric loss. For that, you need a pellet. So for pellet, you have to put this material in the hydraulic press, apply, use that KBR press generally will use. By pressing it, that it's come just like a tablet. You will take some paracetamol or this calpol or something. So dimension will be different. Maybe thickness is 1 millimeter, diameter maybe 10 or 12 millimeter. Depends upon the how much dia and punches you are using in the hydraulic press. That is the thing. And then if you need the electrical measurement further, so do the polishing of the surface, because you need the ohmic contact. So by doing so, you can get the dielectric constant, then dielectric loss, then the impedance value, real part of impedance, imaginary part of impedance, lot of parameters. Now to sophisticated LCR meters are there. You just put it, automatically that data will be transferred to the computer, and you can analyze whatever the parameters you want for your research. And similarly, if you want to study the room above room temperature behavior of dielectric constant and the loss, then you need the small furnace associated with the LCR meter. So you can slowly raise the temperature above the room temperature, so you can see the behavior of the dielectric parameter by increasing the temperature. We did also, so that I am going to tell you later. So this is overall known as solid state reaction process. Similarly, you can prepare your chemical by other chemical analysis method also. So this is the figure shows the methodology. So here what rare earth we have used, one is lanthanum, another one is neodymium. So that's why if you see that the basic materials are bismuth oxide, iron oxide for BFO, and for doping either you take lanthanum oxide or neodymium oxide, and some other like samarium also, yttrium, dysprosium, and so on. For analysis, these are the instrument required. First, for structural analysis, you read XRD. For morphology study, you need FESAM. Elemental, we need EDX, how much element present in the sample. For dielectric and impedance measurement, this LCR meter we have used, this N4L PSM. Then for ferroelectric behavior, we take P-loop tracer study, and for magnetic material, we'll take MH loop by the vibrating sample magnetometer or VSM. Why we take XRD? XRD is nothing just like a fingerprint of human being. And everywhere you are putting your attendance by your thumb or something. Why? Because every individual is having the individual identity by putting your fingers. Similarly, here, if you see the materials, so every material is having unique property in terms of their crystalline structure, then in terms of their stress or small regions. So you can do with the XRD analysis. That's why for the proper structural analysis, this XRD is the fundamental requirement of any study. And earlier, if you remember that, if you go to the history, so earlier, initially, this JCPD file is there. Still, those who are doing research, so they cited if you got some peak in the intensity curve with respect angle, so you can uh, cite some reference of the journal where you can see the some number JCPD. You said that whatever we have done, it's comparable to that published result. But later it was converted to ICD, then later PDF, then PDF version 2 came, where you will get the more than 2 lakh specimen their structural is available, so you can compare whatever you are going to prepare with the standard database in the PDF version 2 of the database. If you see here, we did for pure bismuth ferrite. So here, if you see that this was done with wheel refinement through the foolproof software, the XRD analysis. So here, if you can see that in that figure, this black line and red circles are there. They denote actually the experimental and the calculated data. For the pure bismuth ferrite, there was no doping of any rare earth. Okay, so in ideal cases, pure bismuth ferrite gives which type of XRD structure you can see it. And here at the bottom, you can see this bluish lines are there and the greenish lines will be there. So at the bottom, this blue solid line represent the difference between the observed and calculated values. And similarly, whatever these green lines are there on the above of it, it displays the Bragg's location. If you study the Bragg's law, you know that 2d sine theta is equals to n lambda. So that Bragg's point locations are there with the green lines here. So this is for pure XRD. Now, what we did by doping, suppose in first case, we did the doping of lanthanum in pure bismuth ferrite at the iron side, means B side. So then what happened? You can see it. On first figure, if you see, we have taken the different composition. On the bottom, pure bismuth ferrite BFO is there. Then after that, 10, 20, 30, 40, up to 90% of lanthanum doping at the iron side. But what happened after doping? If you see the enlarged view of the same figure, so it's showing that whatever angle is there, it is moving towards the right hand side. Means what happen? If you are sending some external material on the pure bismuth ferrite structure, so it some distortion occurs in the structure. And how it will reflect? It comes in terms of the structural analysis, where if you see the angle or the peak, it is moving toward the right hand side of the figure. So means something is going on. Suppose, for example, this room is having capacity of 100 students, and suddenly you want to adjust 50 more students within it. How is possible? There may be chance of some overlapping in the structure. Maybe some seat will be shared by two students, maybe three also. So similar things happen with the structure. If you want to deliberately disturb the structure, then something happen. And how you know that? There is a simple formula you can calculate with the tolerance factor. There is a simple mathematical formula. You put the value. In the ideal case, it should be 1. But if there is a distortion, that value should always be lesser than 1. So here, if you calculate, it may be some point 0.75, 0.8 or something like that. So mathematically also you can see that some distortion occur on the doping of external material in the structure. So that is the main motto behind this study in simple term. So similarly, we have done for other purpose also. And how we know that? If you see that here some numbers are coming. Anybody can ask what is 220110. Suddenly you cannot write any number on the peak. It's just nothing. But we did the analysis by a software called POWD. POWD. It was developed by the some Australian university long back ago when I was a research student. But now the original version is disappear. Only you can get the pirated one. So that's why people are using now a Jana software. This full proof is there, expert is there, hundreds of software freely available in the open source. You can use it, but certain times some restriction is there. You cannot get all the parameter with the free one. So for that purpose you need the license one for that. So we use this Pout software to take the HKL values. If you have remember the crystallography where Miller indices is there, so you can represent that 3D plane in terms of HKL value. So these 220110, these are the HKL values corresponding to that peak. But still, some impurity may also be there because it occurred due to the casualness during the preparation. You cannot always keep the ideal atmosphere. So some impurities will be there. So then you can highlight those impurity in the peak during your analysis also. So what we did with this one for all series, you see these are the parameters which we have got it. So why we have taken? Because if you see these values of lattice parameter for each series, we have first calculated this average crystallized size. There is a common formula which is known as Shear's equation, Debye Shear's equation. So you put whatever values you are getting from the XRD analysis, so you can get the average crystalline size for the corresponding series. So you can see that these values lies between 30 nanometer up to 53 or 54 nanometer and so on for the different series. Number first. Number second, if you see that pure bismuth ferrite is rhombohedral in nature, but after doping of this lanthanum, we got the orthorhombic structure. Means after doping of lanthanum in pure bismuth ferroid, its structure changed from rhombohedral to orthorhombic. Means after doping of lanthanum, something is happening within the structure. It confirmed that. Similarly, we have did for another series called neodymium. So again, you see that I put the small figure here and the average lattice parameter ABC, their phase, crystallized size for neodymium. Similarly, we have done for samarium also. Similarly, we have done for yttrium, dysprosium, lot of series. Why? Because our motto is to get the optimized value where we can reduce the leakage current of the material. So you cannot get suddenly by doing experiment. So we want to capture the whole data. So that's why this project was funded by ICRB. So still we are doing work on it. Already I have produced 6 PhD from this work, and I don't know how PhD requires for this. So it's a going on process. Then if you see another analysis we have done, this is FESAM. Why we have done FESAM? Because we want to show the polycrystalline nature of the material. Here for different series, the shape and size of the material is different for the different doping of lanthanum. And even some places you can see the void space is there. Void space means there is a space between the atoms in the structure. And the lower diagram confirm the EDX of the same image. Why EDX? Because it confirms that elemental presence of iron, lanthanum, bismuth in their elemental composition. So it confirmed that whatever reagent we have taken initially, raw material, they is still available in the resultant. There is no external impurity here. If there is any impurity, then that will also come in the picture. So this EDX confirm that there is no foreign element present in this diagram, and we'll get the surface morphology of the sample what we have prepared after the doping of lanthanum, neodymium and others. So this was done through the FESM analysis. Okay. Now in next phase we have coming for dielectric. If you see that, so we have taken the dielectric constant with respect to the frequency at the different temperatures. As I told you, we have a small furnace. It will work from room temperature up to 500 or 550 degree. So by slowly changing the temperature, we can get the dielectric parameter also. And if you have don't facility of that furnace, you can simply do it at room temperature also. So you may get same time, because here if you see, when frequency was low, dielectric constant is high, but at the higher frequency is high, in almost all cases it becomes almost constant. So simple logic is there. If frequency is low, means your material is able to show all type of polarization, electronic, ionic, dipole, and so on. But at the higher side, maybe one or two type polarization is available. So that's why this curve becomes flat or constant. This is the simple behavior of any dielectric material. So similarly, we did for all other series. You can get the same diagram. In another phase, we have seen the dielectric loss also we call 10 delta. And here, another important thing you can get it, that phase transition also takes place. If you see this black curve on the lower figures, where the lanthanum was 20 and 30%, so you can simply get the highest peak. And after is again decreasing with increasing the value of temperature. Means there may be phase change occurs, means your material is showing from ferroelectric to paraelectric phase transition. So you can see that at what temperature it is happening, it is around 425 K. So why we have taken the different temperature? So we want to see that at what temperature phase transition occurs in the material. Means it is changing from ferroelectric to paraelectric phase.